Cybersecurity is an amazing topic to study, and particularly it's an arms race between us and the attackers.
Building systems resilient to cyber attacks is of course a challenge of great practical interest.
Every day there's a new challenge to face.
Strong mathematics, but also a practical point of view. You need both.
Help giving users a more secure experience.
It's like a game because you have two sides, the defender and the attacker.
It is a wide domain. We often necessitate knowledge from other areas, in my case industrial system and machine learning.
The domain is complex and it requires the understanding of heterogeneous data sources and use cases.
And new things to learn.
So cybersecurity is very motivating for me because in cybersecurity you may have some prior knowledge on the nominal behavior of your system, but you have to face attacks that are yet unknown.
Okay, so yeah, as I said before, my name is Marc-Oliver Pahl, and I'm not only running the summer school, but I'm also the chairholder of the chaire Cyber CNI, where we do cybersecurity research, and there are also some people in the audience today that were also in the video and saw it for the first time, I guess. Okay, so with this talk, I want to set the stage, and let's start with critical infrastructures, or with infrastructures that can be attacked. So what are these infrastructures? I put you some examples here. So you see healthcare, water supply, energy supply, communication, data centers, industry 4.0, transport, defense and national security, finance, education, research and innovation, food, and many more. Why did I put exactly these? Because you see cyber physical systems, systems that are computers connected to each other, doing something together, or even being connected to the outside world, are ubiquitous. They're everywhere. They're in the middle of our society, and they're also especially connected to the internet. And this can lead to problems because in the internet, they're not only good people like you and me, but they're also bad people. I symbolize them here in black. And these bad people that are distributed all over the internet can attack the resources in these systems comfortably from their home. And when they attack these systems here, then they do not only attack the systems, but they attack our society because they attack your water supply, they attack your energy supply. And this is, of course, nothing that you want. And therefore, at the chaire, we work on how can we protect against this. And we have different directions we look at. So we look at prevent. So we try to prevent attacks as much as possible. This is so-called security by design. That means we develop mechanisms to protect systems in the best way possible. Now you might say, okay, if you protect the systems in the best way possible, why do you need something else? The answer is you can never protect a system 100% if the system is a system that is flexibly interacting with its environment, because you have programs that change over time. You bring in new devices, you remove devices, you change configurations, you have humans interacting. So you have dynamics that you cannot get rid of, and you also don't want to get rid of because this is exactly the functionality that you want to have. And therefore, the second thing that we're doing is detection. So we look at how can we detect attacks or anomalous behavior of such systems. And when we detect such a thing, then we look at, okay, how can we mitigate from these attacks? How can we have automated defense? How can we bring the user into the loop so that the user is getting the information that he needs in order to understand the system better? So this is what you see with the lights here on the right side. For doing this protection, we use multiple mechanisms. I put you some examples here. So we use also machine learning to do fuzzy data analysis. We use so-called digital twins, so digital equivalents of a physical something to do tests and also to check and understand the systems. We use distributed ledgers to exchange information between untrusted parties. And we also look at ethical algorithms. So how can we design systems, computer programs in a way that they behave ethically? And this is exactly what we will discuss on Wednesday in the last evening session, where Martin Hellman, a Turing Award winner, so this is one half of the Diffie-Hellman key exchange, he will talk to us over the recording and tell us why it's so important to always take such ethical decisions. Okay, now you know a little bit the stage. Let's dive a little bit deeper. So this thing we're talking about is also your smartphone. This is also a cyber-physical system, so something that you carry with you. It's safe driving cars, like the one here. So now the car is driving, and you see that the car is processing its environment, it's collecting data, it's reacting to the environment. If someone hacks it, it might crash into you if it's a self-driving car. And this is, of course, something that you don't want to have. And therefore, security is super important in all the environments I was talking about, and especially also in the Industry 4.0 setting. And here's an example for such an industrial robot as you find it in an Industry 4.0 factory. And I chose this example because it shows you why malfunctions could harm you, because let's see what these guys are currently creating. Yeah, so I fast forward, so this is the end. And so this robot-controlled chainsaw was building two stools and a table, which is of course nice, but now imagine you work with this machine, you're there where the people are right now, and a hacker attacked the machine and is now moving it towards your head. This is obviously nothing you want. Okay, so let's come to the challenges once again. So this is a workshop as you found it at the beginning of the 20th century. What is important for me here is that you have many people. So these here, so I have lots of them. And you have machines that are doing a job there and they're isolated. And people are taking the goods and carrying them from one post to another. This is what characterizes the industry. Also at the beginning of the 21st century, it was more automation. But the key aspect here is you have isolated systems that are interacting with the humans, and you do not have full automation. When we switch now to a modern workshop, which is this one, you see that there's at the moment an industrial robot coming. There is way less people, as you see here in the back. And what is important here, that everything is networked. So you have distributed sensors and actuators, and they're all connected and also connected to computer programs and doing something there. And this is a big paradigm shift. So let's have a look at why. So this is now a modern factory. So you see at the bottom that you have the machines that interact with you and interact with the humans. And on top of that, you have the controllers here. And on the right side, you have the network. Okay, so that means inside the factory, everything is connected. Good, but it doesn't stay inside the factory. Typically, the factory is also connected to the so-called cloud, where you have servers, and then more recent paradigm is the edge, where you have also servers that are used for broader areas, but are closer to you, which is from a security perspective good, from a latency perspective as well. So what is the problem now? You don't only have one factory, you have multiple factories. They are connected over this internet, which is good because we exactly want to have the services that are offered through this connection. But the problem is, when you look at the attack surface, at the beginning, when everything was isolated, you had so-called insider attacks. So people inside the factory could do attacks. Of course, you don't want that. But if you have a good company culture, or if there are not many of them, you can limit this. You can also do physical access control and some other things. When we go to the edge fog, the setting is changing. So there are already more people because it's more attractive and it's also closer to the internet to do attacks there. And when we then finally go to the internet, then we see, okay, there are lots of attackers simply for the rules of statistics. So they are just more humans, and they are capable of attacking, as I said at the beginning. So what are the security problems now? I put you 3 examples. So the first one I simply call security. And what is this about? Well, this is about you have your factory, and then someone is attacking the factory, and then your production is not working, your factory is stopping, you're losing money. Of course, this is nothing you want. The second, to me more important, safety. So you have human workers, and these human workers are interacting with the robots. And as we've seen with the robot arm controlled chainsaw before, this bears, of course, a risk, and therefore you have to take care of that. And the last point I put here is privacy, because we've seen before cameras. So this is again something that these IoT systems by design have to interact with the environment, because you want to have context-sensitive services. You want to have services that react to what is happening around them, and therefore they have to collect data. But of course, you do not want everybody to know when you go to work, what exactly you do, see your image when they want to remotely access you, and so on. Therefore, privacy, super important as well. Okay, so now we have a little bit abstract attacks. I bring you now 4 example attacks, and then Lars will detail to you the first one I come to. You definitely heard of. So it's the Stuxnet attack. And I will not go into detail to these attacks now, but as said, you have the slides afterwards. On the right side, you see some of the interesting questions, and you also have some starting links. So this is something to look at, an important and interesting cyber attack. The second one I want to mention is the flame attack. Here you can also have a look. The third one is the so-called HAVEX attack. Also an overview on that. And the fourth one I want to mention and give you the hint to look at it when you're interested at home is the black energy attack that is given here. And that said, I hand over to Lars, who will take you through the more details of the Stuxnet attack. Lars.
Thank you very much. I hope that. So I guess, yes, most of you will have heard of Stuxnet before. It's a malware, or, well, the first malware discovered. I'm not sure. I cannot press forward.
You cannot. Maybe you have to click again on the image. If not, I can press it. You can just tell me.
Yes, please go ahead. Yes, so it's a very rather sophisticated malware, and the first digital cyber weapon that was actually used to attack some physical infrastructure. In this case, this was the Iranian nuclear program, and it was then uncovered in 2010 when it broke wild, because the creators made some mistakes in the spreading mechanism they used, and then it went almost everywhere or infected many systems. I'm not sure if you used the computer back in the day, then your antivirus software might have found it after it was uncovered. It was initially built so it spread over the network, but it ultimately compromised the programming logic controllers in the enrichment side and manipulated the behavior to break different centrifuge. How that was done, we will get to later. Yes, but well, it was highly tailored at specifically this enrichment plants in Iran. And as you can see in the picture here, you can see that there's almost no doubt that Iran was the target of this attack. After it was uncovered, it was extremely well studied. I guess nowadays you cannot read any paper on security of cyber physical systems without stumbling upon Stuxnet. there's an extensive technical report by Symantec, and I goes very much into the details of what or how the malware worked. And then there's also a book by Kim Setter, who did the geopolitical assessment of Stuxnet, who might have been the actors or who probably was the actor, and working on that, and then created the malware. So on the next slide, we will see the path that was taken to breaking, well, lots of the centrifuges that are used to enrich the uranium for nuclear, to develop nuclear weapons. Well, the layers that we all know, the IT layer, on which, well, we have the network itself, operating systems and different applications running on the computers. And, well, the first goal, of course, is, well, to infect these computers, which then can distribute further. Well, basically, the goal is to get onto the PLCs and manipulate the routine such that the centrifuges will break. A very, very important aspect of Stuxnet was that it was deeply undercover. So a main emphasis on the development or on the functionality was that it remained undetected. And, well, once we are on the target machine, we can concentrate on getting ahead onto the ICS layer, or well, where the industrial controllers are, or the subcontrollers controlling different valves. And there we want to manipulate the control such that other commands are sent or executed then intended to damage that on the physical layer where the devices themselves are. And yes, ultimately our goal was, or the goal was to break it. So first step on the next slide is the infection of the machine. So Stuxnet targeted specific 32-bit Windows versions. There's a control flow where it just went onto the machine, then checked the bit, the operating type, the architecture. Well, in case it did not have any administrator privileges, it did some privilege escalation and then continue. And then this was one of the first very interesting is that it checked for the running processes, amongst which the running antivirus software, and it would hide differently and behave differently depending on the software that was installed on a computer to remain undetected. After that, it ran the DLL also, so it was all delivered in a DLL. And after it started to check for internet connectivity, and if there was internet, well, it connected to a specific command control server with some specific domains to send information about the system it is on and receive also commands from remote. The interesting thing there, it had also some peer-to-peer capabilities. So it also checked the network for other computers, first to infect it, but also to update itself in case it did not have the newest version. And yes, so the goal after establishing itself on the machine is, well, just infect other computers, which is on the next slide then. So we have we want to propagate through the network. Well, first of all, as I mentioned, we have some peer-to-peer communication where we could update others or get ourselves updated, infecting special computers with control software. So when CC machines there, they often had a hard-coded password in it, which was publicly known. And it infected network shares. So everything there. There were 2 0 days that were used. So first through a print spooler, which was, well, it was a 0 day, which was not patched, but it was publicly known before. And then a unknown service, so in the Windows Server service. And later, the latest, so most of the time, in order to infect air-gapped systems, it could also install itself on or hide on USB sticks and get there and then propagate through USB sticks. There, it was very interesting that this phase had a timer on it, so it only ran through for a couple of weeks before uninstalling itself if it was unsuccessful or receiving a special command. And also on the USB drives, it infected, it only it had a counter in it counting to 3, so it would only install 3 times or infect 3 machines. What is very interesting about that as well, so the propagation methods changed throughout the different versions of Stuxnet. So in the beginning, it was limited to the removable drives and the peer-to-peer functionality in the Windows Server in principle, and the network shares were not affected in the first versions and only were added later on in later versions in which it then has gotten out of hands. So yeah, so now the next step is when we have infected ourselves and we are on the computer and do so we want to get onto the next layer, so the ICS layer. And that's on the next slide where we have the manipulating of the industrial controls themselves. So Stuxnet targeted a specific version of the Siemens industrial software for industrial controllers called Step 7. And therefore it skimmed through the file system and looked for to the installed programs and looked for specific installations of Step 7 and infected very certain or specific project files. So as before, it is a highly tailored malware that was only targeting these enrichment plans. So it installed itself there and manipulated different project files to modify the logic on the PLC itself in case they are connected. It went even that far that it reprogrammed or overwritten basic functionality for PLCs that are usually default on board, and even despite still hiding itself. So Stuxnet was also the first version of a rootkit for program PLCs. And so then once we are on the PLC, of course, we also want to do our thing, yeah. And Stuxnet had a very specific way of working. So if we continue on the next slide, we have a state machine of the attack, and initially we are in state 0, where we wait for a few hours, and then are installed or start executing. And after a few, if we're in that state, Stuxnet still remained silent. It just listened in the network and on the PLC looking for actions, what was going on, and collected this data to use for later on. After it collected enough data, I mean, this could be any amount of time between 13 days or 3 months, depending how active or how much activity was on there. And then it went to the next day, waited for 2 hours and did nothing, waiting for another. So collecting or reassembling that to mimic the behavior of the PLC for later on, during the time frame in which it actually manipulated the valves and centrifuges. And in the next stage, so we're now in the third state, the rotation speed of the centrifuges was accelerated. The valves were closed a little to increase the pressure within that keep the gas or in the centrifuges in a certain state to make this gas also unusable. And then after 15 minutes, just go back to normal. And this time, the commands were sent to the centrifuges from the PLC, and the output was from the centrifuges was also monitored. However, the output was also overwritten such that it appeared for the operators of the plant that nothing would happen, and the operation was quite normal. Also, the changes were very, very tiny, so they were looking for specific frequencies for the centrifuge to operate on, which were damaging. And after a while, so since there were lots of tests by the IAEA, so the atomic agency supervising the nuclear program in Iran, the auditors began noticing that lots of centrifuges were breaking. And first of all, this was a very tiny amount of centrifuges breaking, but these checks were done every 3 months. And more centrifuges kept breaking at a very unusual rate. So there, first of all, it was said that there are some malfunctions and they tried to cover it up. But after a while, it became clear that there's something wrong, and they were trying to find the root cause. And at the beginning, it appeared that there was no root cause that could be found, but it continued to break. And after a while, Symantec went public to announce that they have found Stuxnet, because apparently the versions had changed again, and it spread wildly to lots of machines that were not intended to have it. And that's when the Iranian government found out that Stuxnet was actually targeting their nuclear program. Well, after this, we're on the fourth state, where everything went back to normal, and then Stuxnet went back to being quiet and waiting for another, and going to state 0 again. Yes, if you want to read more about that, I've put some references on the side there. So these are some extensive reports. If you're very interested in that, there's a lot to learn from that. So, Marc-Oliver, thank you very much. Thank you for listening, and take it away.
Thank you very much, Lars. And you can already note down the questions for him, because I'm sure there are more questions, and I can highly invite you to study such attacks, because you learn a lot about the systems that are getting attacked. Okay, so yeah, this brings us to the defense side. So what can we do against such attacks? So I said it at the beginning already, we can do security by design, securing the systems as much as possible, starting from the users, going down to the physical protection. Then on top of that, we can do automated monitoring and defense. So looking at if something strange is happening here, machine learning can help us, for instance. And then on top of that, we have to have the human in the loop, because security is nothing clear in the sense, okay, this is exactly how security has to be done, but it's something that grows with the policies that the users want to have in the systems they want to secure. At the chair, we of course cover all these topics. So I told you already, prevent is important, and you see in the animation on top with the attackers that they are getting less through the activities that we do. So prevention protects against lots of attackers already. Detection helps us to understand the systems. And then the automated defenses, this is something that is helping to minimize the attack risk. So now I brought you once again some of the members of my chair telling you what they are at the moment working on.
Industrial systems.
Formalization of resilient systems.
Security risk optimization for learning on heterogeneous quality data.
The management of access control in IoT infrastructure.
Safety and security.
Threat analysis.
Diagnose incidents.
enhance situational awareness of cyber analysts.
Random distortion testing, RDT in short.
Traceability and integrity of information.
Platforms for research purposes.
Values from sensors, actuators, and automata.
Detection of anomalies.
NFV, which is network function virtualization.
Critical systems.
Risk analysis methods based on extension of attack graphs.
Anomaly detection in physical data from the Secure Router Treatment Testbed SWAT.
Network intrusion detection system.
Access control policies on IoTs.
Machine learning to design IDs.
Okay, so you see there's a broad range of activities, and on this slide here I brought you some of the topics we're currently working on. I will not go into detail, but as you see, it goes from the prevention side to the user interface side, where we have some 3D interfaces, and to come to the end of the presentation, I brought you some videos from the infrastructure that we are running at the chair, because we have quite nice test beds for doing our security research, and I will just start the videos. So here on top you see some Fischer Technic factory emulators. These are tiny factories that are controlled by the real PLCs, by the so-called programmable logic controllers, the things that were attacked in last scenario. And here we have a factory. We can look at what happens when there are some attacks, how can things be changed, what are the effects of changing something physically, and so on. And as we have the real PLCs, we can really look at the attacks and do not only have something that is simulated, but we have the physical interfaces that you also have in a real factory, like with the robots we've seen before. Then the second point, this is another version of it. We also look at electrical signals, as you see here. This here is a very similar approach, but here the effects are purely simulated. So here we see a cream factory. Again, the control comes through these industrial controllers. Of course, we also do simulation internet measurements. For that one, we have servers. Then we have real heating devices here, where we can do changes. And this is a heating circle. Oh, no, it's not. So this is a motor, and next to it is a heating circle. So here we have a motor where we can do changes. This is a real heating circuit where we can change configurations. Here you see the water tanks, and you see the actual heater. So the camera goes there now here. This one here is a test bench for these industrial controllers. Here you see the virtual reality interface we're working on. And here in Rennes, we also have a fab lab where you can do 3D printing and similar things. So this is quite cool. And yeah, this is a little bit the Rennes campus here. Okay, so now you get an idea what we're doing. We have now a footer where you also see an animation where we currently are, because we are physically in Rennes. You see the map where this is. And then afterwards, we will put you into the breakouts for 5 minutes. And I will tell you again in a second. You can already start thinking about your questions, or if not, you can enjoy the ending video of this presentation.
the slides you said that there are lots of security and safety things that have to be considered. And then you also mentioned these along with security by design. How do you think of all the things in the first place, and how do you incorporate that into the design?
So thank you very much for this very good question. So how do you incorporate it into the design? So this is an interesting question in that sense that the design is a huge process. So it's not just one step, but you have to introduce it from the beginning, where you think about what you want to do with your product, which is, for instance, when you think about privacy, which is the information that you will collect, why do you want to collect it, which is the principle of least data sharing, least data storing, least data processing. Then, of course, when it comes to the algorithms and the software that you're running, then a super important thing is applying security standards in the right way. So in the right way is the challenging thing here, because you have complex systems with different components that interact, and you have to create then the links in between the system parts that they are secured and so on. So this, and it does not end there. So it's also running the program later. So it's throughout the entire life cycle, and it's through a bunch of different questions that are important to take into consideration. Okay, so I don't know, do we have something else from the chat? Because if not, I'm also not unhappy, because then we can switch to Niels.
Yeah, actually, I have two questions here that were written, so I can read them for you if you want. So the first one is, what are the major reasons for IoT security breaches? Which layer is the most vulnerable?
So I would say the major reasons why IoT is so vulnerable is the distributedness of the systems, which introduces complexity. So you have to take into consideration when a part of your system here is broken, the entire system is broken. And the second major point I would mention is heterogeneity, because you have lots of heterogeneous devices that you bring in, and the weakest part of the chain is defining the security that you have. So this will be my quick answer to that.
I have another one. It's about the Iranian facility. So the question is, did the Iranian facility have some security measures in place which the authors of the malware had to overcome, or they relied mostly on the internet air gap?
So I hand over to my Stuxnet expert, Lars.
So there's a combination of both. Of course, they had the air gap things, and so the creators of Stuxnet got very lucky, because in order to create such a tailored malware, you have to have a lot of knowledge of the system, and they got lucky and intercepted some of the devices, and they kind of built a replica of the plant by themselves, for themselves, and then developed the malware. And yes, they had to overcome also security. As mentioned, they actively hid their files or their activity from the antivirus software. There was also AV software, which Stuxnet was not compatible with. So in case it was found this thing, then it would uninstall itself immediately again. I hope this answers the question.
Very good. Thank you very much. Yeah, and so this probably concludes. There's one more question, yes.
Yes, one more. What is a resilient system, and how is it different from any other information system, and the need to make all IS resilient? Is it IoT specific term?
Yeah, and so my answer to that is, of course, it's not an IoT specific term. So resilience basically means that you build a system that even under attacks and unforeseen situations, the system is still delivering its service. And this is what resilience is. And again, for the IoT, it's a even bigger challenge than for other systems because of the heterogeneity and distributedness that has resource limitations and so on. Okay, perfect. Good. Then thank you very much. Thank you very much, Nicolas.